This video is going to be the introduction to named distributions. We're going to do one named distribution at a time, and we'll start with the Bernoulli distribution. So we'll do a quick recap about distributions in general, and then we'll introduce the idea of a random variable. But if you need some written words about it, a reference for this, go check out our book Biostat, and specifically chapter 3. And don't skip the introduction. I don't particularly like that they define the word random variable in the introduction, but that's what they do. And then continue on to the subsection 3.1.1. And if you want to at least see the math behind some of the details of distributions, continue on to sections 3.1.2 and 3.1.3. But I would ask that you at least do up to and including section 3.1.1. So then we'll start into the Bernoulli distribution after we introduce a random variable. And the subsection you can read for the Bernoulli distribution is in the same Biostat book, section 3.2.1. So distributions, as far as we have been concerned, is the shape of the population of interest. So that is to say, if we are interested in some population distribution, well, it could be right skewed. Or we could have a population distribution that is symmetric and unimodal, just has one mode, just has one hump in it. Or we could have some population distribution that is left skewed. So any of these are distributions of the population of interest for whatever variable it might be. Specifically, the distribution represents like the shape of all of the things of interest as plot in, say, like a histogram or a density plot. Okay, so that was our quick recap of distributions. We're going to start tying that to observed data. And the way we tie these distributions to observed data is through the idea of a random variable. So let's just introduce that next. A random variable holds a few different ideas in mind for us. A random variable is essentially a variable whose outcome is unknown. Hence, it's random. A really simple particular example is just a coin flip. If I flip a coin, you can't tell me consistently what outcome we will observe. You might be able to tell me one or even two or maybe even three times in a row, but you can't really extend beyond that, or at least I'd be willing to bet a lot of money that you can't tell me 5 times in a row the outcome of a flipped coin. So a random variable is really just a variable whose outcome is not yet known. And this could be anything like a coin or even a human being. You yourself are a random variable to me in terms of your height. Well, not only the semester because I literally don't see you standing in front of me, but also because I don't have a tape measure out and I haven't actually observed your height with an appropriate tool. Until I observe your height appropriately, you are a random variable for, in fact, a variety of different outcomes: height, weight, even simple things like major. So a random variable in the simplest case is just a variable whose outcome is unknown. But in another sense, a random variable is a quantity that describes or is drawn from, is like taken from the population distribution of interest. So random variables can follow distributions. The phrase we use is follow distributions, but what we mean is like this random variable is a member of that population. And that population is described by some shape, some distribution. So essentially the random variables follow that shape. Okay. In another sense, random variables define the relationship between possible outcomes and the probability of those outcomes. Sorry that the word outcomes is smushed down there in the bottom, but that's okay. I think you get the idea. Random variables have outcomes whose are unknown. They follow specific populations. That is, these random variables are theorized to come from a specific population and hence follow that population's distribution. And they define implicitly the relationship between the set of possible outcomes and the probability of those outcomes. So I think the easiest thing to do is jump into a quick example for like the Bernoulli. So let's just move to the Bernoulli distribution. And again, we'll start real simple. The simplest example of a Bernoulli distribution is a fair coin. A fair coin with probability of heads equal to 1. Whoops, 1/2. My mistake. A fair coin has probability of heads equals to 1/2. That's what makes it fair. So if we were to phrase this in terms of a Bernoulli distribution, we would say a random variable is Bernoulli or follows the Bernoulli distribution if, now think of a coin, there are only 2 outcomes. Now to generalize for the Bernoulli random variable, we don't say there's just heads and tails, we say there's outcomes 0 and 1. And we often associate that with, in order, tails and heads. So that tails is 0 and heads is 1. That's just kind of a custom in the world of statistics. There's no real reason behind associating 1 with heads. Okay, so we have a Bernoulli distribution if there's only 2 outcomes and the probability of the observed outcome 1, keep in mind heads if it's easier to imagine a coin, is P, whatever that probability might be. In the case of a coin, specifically a fair coin, that probability of 1, heads, the probability is 1/2. But generally, we have a probability P, whatever number that might be between 0 and 1, is associated with the outcome 1, and hence the probability of 0 is 1 minus P, since we need our probabilities to sum up to 1, just like 1/2 for a fair coin of observing heads plus 1/2 of observing tails is 1. In the same way, we have P plus 1 minus P will just give us an outcome of 1. So how about another particular example? We'll keep 2 boring examples for just a minute. An unfair coin with P equals to, I don't know, let's say 1/4. That makes a Bernoulli random variable because, again, there's just 2 outcomes. And it's an unfair coin because the probability of observing heads is 1/4, not 1/2. Okay, but we can have more exciting examples like a randomly selected tomato seed is implicitly a Bernoulli random variable if we're interested in whether or not the seed will germinate. Since there's only 2 outcomes, the seed germinates or it does not, it is inherently a Bernoulli random variable. And because there is some unknown probability that the seed will germinate, we know there's this probability P, whatever it might be on the population side, to describe this random variable and this distribution. Let's be a little bit more specific. Some probability P, the seed will germinate. Now, the way statistics goes is we recognize there is this population of tomato seeds. Even if we don't have all the tomato seeds in the world, there is a population of them. Okay, to learn about that population's characteristics, i.e. the parameters, that's the value P in this example, you would take a random sample of tomato seeds. You would give them some sort of treatment. I don't know, sunshine and water put in dirt. And you'd put the seed in dirt and then give them sunshine and water. And then you'd measure how many of those seeds actually germinated. Because you'd have a bunch of zeros and ones, 0 if a particular seed did not germinate, and 1 if a particular seed did germinate, you'd essentially just take the mean of all of your outcomes. 1 anytime the seed germinated, 0 anytime it didn't, add up all the zeros and ones, and divide by however many there are. That would give you an estimate of the population parameter P. You would have a little guess, P hat, of the population parameter P. Let's try to do that in I don't know, R, our favorite new tool for making up data. R is particularly good at generating fake data. That is, we make believe that we know all the things about the population and then generate some data. And then we can use the tools of this class to kind of show you how we can learn about those population parameters. So let's just do a quick example. There's a function in R that's named R binom. Now the R stands for randomly generate, and binom we will learn about in a future video. But for now, let's just go with it. The arguments to R binom in the case of a Bernoulli are how many observations you want. Let's just say 3. And then for a Bernoulli, you will always put 1 for the size. And then you'll put the probability of whatever process it is that you are pretending, in this case, because we're pretending like we know the population distribution and all of its parameters, you'll put whatever probability you think the population should have. So I'm okay at growing tomatoes, so I'm going to say there's a 75% chance any of my randomly selected tomato seeds will germinate. So what we're going to do here is pretend like we've taken 3 seeds. We'll leave this as 1 for now. We'll kind of explain what it means in a new video. And there's a probability of success that any one of the 3 seeds will germinate equal to 0.75. So let's see how it goes. So on my first random sample, I had 1 seed that did not germinate and 2 seeds that did germinate. Let's try imagining that I have 5 seeds now. Just by chance, because there's a high probability of success, all 5 seeds in this made-up example germinated. Let's go one more time just to show you that it's truly random. And this time 4 out of 5 seeds germinated. Now what I'm claiming is that if we take the mean of our observed data, we will estimate the true population parameter. In this case, because it's completely fake, we know what the true population parameter is. In the real world, we won't know this highlighted value, P, but we will have observed data from which we can try to estimate that observed value. Okay, so let's do something a little bit more interesting. We'll say I took a random sample of 50 seeds. I'll store my data into a variable named X. You can see over here on the top right that sometimes the seeds germinated, sometimes they didn't. Here's a long streak of them germinating, and here's another one that did not. And indeed, there's 50 observations. So we could create a new variable named p hat by calculating the mean of x. So here I'm going to name my variable p hat, like I am guessing the population parameter p. I'm going to assign into that variable the outcome of the function mean calculated on the vector x. And look, p hat is a guess of the population parameter, 0.75. It's not perfect because we don't have all the tomato seeds in the world. We just have some. But in the theory of statistics, if we sample more observations, then theoretically we're going to get closer to the true population mean. Now that doesn't always work out in our favor, but it should work out often enough. Like this one's actually slightly closer, but not by a lot. And theoretically, if we take a ton, look how easy that is in R, of new samples, of new observed data, then we can get really close to the true population parameter. So this was our first named distribution. It is the Bernoulli distribution. And it's fairly easy to replicate, or no, not replicate, to create some fake data in the world of R such that we can get a better understanding of both the random variables themselves, the observed values, and the population parameter describing the probability that any one of these outcomes is equal to 1. Please do give yourself a quick example of something just like these 3 lines of code. Pick your own population parameter P, maybe play around with a few different sample sizes, and convince yourself that as your sample size gets bigger, your estimate will get closer to the population parameter of interest.